Labyrinthodontia is an extinct amphibian subclass which constituted some of the dominant animals of late Paleozoic and early Mesozoic eras. The group evolved from a lobe-finned fishes in the Devonian and is ancestral to all extant land-living vertebrates. As such, it constitutes an evolutionary grade rather than a natural group. The name describes the pattern of infolding of the dentin and enamel of the teeth, which are often the only part of the creatures that fossilize. They are also distinguished by a heavily armored skull roof and complex vertebrae, the structure of which is useful in older classifications of the group. Because labyrinthodonts do not form a monophyletic group, many modern researchers have abandoned the term. However, some have continued to use the group in the classifications, at least informally, pending more detailed study of the relationships. Labyrinthodont traits. The labyrinthodonts flourished for more than 200 million years. Particularly the early forms exhibited a lot of variation, yet there are still a few basic anatomical traits that make the fossils very distinct and easily recognizable in the field. The labyrinthodonts in life. General build. Labyrinthodonts were generally amphibian-like in build. They were short-legged and mostly large-headed, with moderately short to long tails. Many groups, and all the early forms, were large animals. Primitive members of all labyrinthodont groups were probably true water predators, and various degrees of amphibious, semi-aquatic and semi-terrestrial modes of living arose independently in different groups. Some lineages remained or became secondarily fully aquatic with reduced limbs and elongated, eel-like bodies. Skull. With the exception of the snake-like asteropods, the skulls of labyrinthodonts were massive. The broad head and short neck may have been a result of respiratory constraints. Their jaws were lined with small, sharp, conical teeth, and the roof of the mouth bore larger tusk-like teeth. The teeth were replaced in waves that traveled from the front of the jaw to the back in such a way that every other tooth was mature, and the ones in between were young. All teeth were labyrinthodont. The sole exception were the chisel-like teeth of some of the advanced herbivorous diadectomorphs. The skull had prominent otic notches behind each eye and a parietal eye. Postcranial skeleton. The vertebrae were complex and not particularly strong, consisting of numerous, often poorly ossified elements. The long bones of the limbs were short and broad, and the ankle had limited mobility, and the toes lacked claws, limiting the amount of traction the feet could produce. This would have made most labyrinthodonts slow and clumsy on land. In adulthood, most of the largest species were likely confined to water. Some late Paleozoic groups, particularly microsaurs and seymouriomorphs, were small to medium-sized and appear to have been competent terrestrial animals. The advanced diadectomorphs from the late Carboniferous and early Permian were fully terrestrial with skeletons, and were the heaviest land animals of the time. The Mesozoic labyrinthodonts were primarily aquatic with increasingly cartilaginous skeleton. Sensory apparatus. The eyes of most labyrinthodonts were situated at the top of the skull, offering good vision upwards, but very little lateral vision. The parietal eye was prominent, although there is uncertainty as to whether it was a true image-producing organ or one that could only register light and dark. Like that of the modern tuatara, most labyrinthodonts had special sense organs in the skin, forming a lateral line organ for perception of water flow and pressure, like those found in fish and a number of modern amphibians. This would enable them to pick up the vibration of the prey and other waterborne sounds while hunting in murky, weed-filled waters. Early labyrinthodont groups had massive stapes, likely primarily anchoring the brain case to the skull roof. It is a question of some doubt whether early terrestrial labyrinthodonts had the stapes connected to a tympanum covering their otic notch, and if they had an aerial sense of hearing at all. The tympanum in aneurons and amniotes appear to have evolved separately, indicating most, if not all, labyrinthodonts were unable to pick up airborne sound. Respiration. The early labyrinthodonts possessed well-developed internal gills as well as primitive lungs, derived from the swim bladders of their ancestors. They could breathe air, which would have been a great advantage for residents of warm shoals with low oxygen levels in the water. There was no diaphragm, and the ribs in many forms were too short of space too closely to aid in expanding the lungs. Likely air was inflated into the lungs by contractions of a throat sac against the skull floor like in modern amphibians, which may be the reason for the retention of the very flat skull in later forms. Exhalation with the aid of the ribs probably evolved only in the line leading to amniotes. Many aquatic forms retained the larval gills in adulthood. With the high atmospheric oxygen and carbon dioxide pressure, particularly during the Carboniferous, the primitive throat sac breathing would have been sufficient for obtaining oxygen even for the large forms. Getting rid of carbon dioxide would present a greater problem on land, and the larger labyrinthodonts probably combined a high tolerance for blood carbonic acid with returning to the water to dissipate the carbon dioxide through the skin. The loss of the armor of rhomboid scales of the piscine ancestors allowed for this, as well as additional respiration through the skin as in modern amphibians. Hunting and feeding like the Sarcopterygian ancestors, the labyrinthodonts were carnivorous. The rather broad, flat skulls and hence short jaw muscle would however not allow them to open the mouth to any great extent. Likely the majority of them would employ a sit-and-wait strategy, similar to that of many modern amphibians. When suitable prey swam or walked within reach, the jaw would slam shut, the palatine tusks stabbing the hapless victim. The strain put on the teeth by this mode of feeding may have been the reason for the reinforcing labyrinthodont enamel typifying the group. Swallowing was done by tipping the head back, as seen in many modern amphibians and in crocodiles. Evolution of a deeper skull, better jaw control and a reduction of the palatine tusks is only seen in the more advanced reptile-like forms, possibly in connection with the evolution of more effective breathing, allowing for a more refined hunting style. Reproduction. The labyrinthodonts had an amphibious reproduction. They laid eggs in water, where they would hatch to tadpoles. They would remain in water throughout the larval stage until metamorphosis. Only the metamorphosed individuals would eventually venture onto land on occasion. Fossil tadpoles from several species are known, as and eotenic adults with feathery external gills similar to those found in modern amphibian tadpoles and in the fry of lungfish and bichirs. The existence of a larval stage as the primitive condition in all groups of labyrinthodonts can be fairly safely assumed. In the tadpoles of Discosauruscus, a close relative of the amniotes, are known. Groups of labyrinthodonts. The systematic placement of groups within Labyrinthodontia is notoriously fickle. Several groups are identified, but there is no consensus of the phylogenetic relationship. Many key groups were small with moderately ossified skeletons, and there is a gap in the fossil record in the early Carboniferous when most of the groups appear to have evolved. Further complicating the picture is the amphibian larval adult life cycle, with physical changes throughout life complicating phylogenetic analysis. The Labyrinthodontia appear to be composed of several nested clades. The two best understood groups, the Ichthyostegalia and the reptile-like amphibians, have from the outset been known to be paraphyletic. Tellingly, Labyrinthodonts systematics was the subject of the inaugural meeting of International Society for Phylogenetic Nomenclature. Ichthyostegalia. The early Labyrinthodonts are known from the Devonian and possibly extending into the Romer's Gap of the early Carboniferous. These Labyrinthodonts are often grouped together as the order Ichthyostegalia, though the group is an evolutionary grade rather than a clade. Ichthyostegalians were predominantly aquatic and most show evidence of functional internal gills throughout life, and probably only occasionally ventured onto land. The polydactylous feet had more than the usual 5 digits for tetrapods and were paddle-like. The tail bore true fin rays like those found in fish. The vertebrae were complex and rather weak. At the close of the Devonian, forms with progressively stronger legs and vertebrae evolved, and the later groups lacked functional gills as adults. All were, however, predominantly aquatic, and some spent all and nearly all their lives in water. Reptile-like amphibians. An early branch was the terrestrial reptile-like amphibians, variously called Anthracosauria or Reptiliomorpha. Pteropods has been suggested as the earliest member of the line, indicating the split may have happened before the Devonian Carboniferous transition. The skulls were relatively deep and narrow compared to other Labyrinthodonts. Front and hind feet bore 5 digits on most forms. Several of the early groups are known from brackish or even marine environments, having returned to a more or less fully aquatic mode of living. With the exception of the diadectomorphs, the terrestrial forms were moderately sized creatures that appeared in the early Carboniferous. The vertebrae of the group foreshadowed that of primitive reptiles, with small pluricentra, which grew and fused to become the true centrum in later vertebrates. The most well-known genus is Seamoria. Some members of the most advanced group, the Diadectomorpha, were herbivorous and grew to several meters in length, with great, barrel-shaped bodies. Small relatives of the Diadectomorphs gave rise to the first reptiles in the late Carboniferous. Temnospondyli. The most diverse group of Labyrinthodonts was the Temnospondyli. Temnospondyls appeared the late Devonian and came in all sizes, from small salamander-like stereospondyli that scurried along the water's edge and undergrowth to giant, well-armored Archegosauroidea that looked more like crocodiles. Prionosuchus was an exceptionally large member of the Archegosauridae, estimated to have been up to 9 meters long. It is the largest amphibian ever known to have lived. A temnospondyl's forefoot had only 4 toes, and the hindfoot 5, similar to the pattern seen in modern amphibians. Temnospondyls had a conservative vertebral column in which the pluricentra remained small in primitive forms, vanishing entirely in the more advanced ones. The intercentra bore the weight of the animal, being large and forming a complete ring. All were more or less flat-headed with either strong or secondarily weak vertebrae and limbs. There were also fully aquatic forms, like the Vinosauria, and even marine forms such as the Trematosauridae. The Temnospondyli may have given rise to the modern frogs and salamanders in the late Permian or early Triassic. Lepospondyli, a small group of uncertain origin. The Lepospondyli evolved mostly small species that can be found in European and North American Carboniferous and early Permian strata. They are characterized by simple spool-shaped vertebrae formed from a single element, rather than the complex system found in other Labyrinthodont groups. Most were aquatic and external gills are sometimes found preserved. The Lepospondyli were generally salamander-like, but one group, the Astopida, was snake-like with flexible, reduced skulls. Some microsaur lepospondyls were squat and short-tailed and appear to have been well adapted to terrestrial life. The best-known genus is Diplocaulus, a nectaridian with a boomerang-shaped head. The position of Lepospondyli in relation to other Labyrinthodont groups is uncertain, and it is sometimes classified as a separate subclass. The teeth were not labyrinthodont, and the group has classically been seen as separate from the Labyrinthodontia. There is some doubt as to whether the lepospondylus form a phylogenetic unit at all, or is a waste bin taxon containing the pedomorphic forms and tadpoles of other labyrinthodonts, notably the reptile-like amphibians. Evolutionary history. The labyrinthodonts have their origin in the early Middle Devonian or possibly earlier. They evolved from a bony fish group, the fleshy-finned Rhipodistia. The only other living group of Rhipodistans alive today are the lungfish, the sister group of the land-living vertebrates. Earliest traces of the land-living forms of fossil trackways from Zakolmy Quarry, Poland, dated to 395 million years ago, attributed to an animal with feet very similar to Ichthyostega. Swamp predators. By the late Devonian, land plants had stabilized freshwater habitats, allowing the first wetland ecosystems to develop, with increasingly complex food webs that afforded new opportunities. The early labyrinthodonts were wholly aquatic, hunting in shallow water along tidal shores or weed-filled tidal channels. For the piscine ancestors, they had inherited swim bladders that opened to the esophagus and were capable of functioning as lungs, allowing them to hunt in stagnant water or in waterways where rotting vegetation would have lowered oxygen content. The earliest forms, such as Acanthostega, had vertebrae and limbs quite unsuited to life on land. This is in contrast to the earlier view that fish had first invaded the land, either in search of prey like modern mudskippers, or to find water when the pond they lived in dried out. Early fossil tetrapods have been found in marine sediments, suggesting marine and brackish areas were the primary habitat. This is further corroborated by fossils of early labyrinthodonts being found scattered all around the world, indicating they must have spread by following the coastal lines rather than through freshwater only. The first labyrinthodonts were all large to moderately large animals, and would have suffered considerable problems on land, while they retained gills and fish-like skulls and tails with fin rays. The early forms can readily be separated from Rhipodistan fish by the clitherum scapular complex being separate from the skull to form a pectoral girdle and carry the weight of the front end of the animals. They were all carnivorous, initially eating fish and possibly going ashore to feed off washed-up carrion of sea animals caught in tidal ponds, only later turning into predators of the large invertebrates of the Devonian at the water's edge. The various early forms of a convenience grouped together as Ichthyostega, while the body shape and proportions of the Ichthyostegalians went largely unchanged throughout their evolutionary history. The limbs underwent a rapid evolution. The Proto Pteropods, like from Elganoerpetin and Tiktaalik, had fin-like extremities with no clear fingers, primarily suited for movement in open water, but also capable of propelling the animal across sandbanks and through vegetation-filled waterways. Ichthyostega and Acanthostega had paddle-like polydactyl feet with stout bony toes that also would have enabled them to drag themselves across land. The aquatic Ichthyostegalians flourished in tidal channels and swampland through the remainder of the Devonian, only to disappear from the fossil record at the transition to the Carboniferous. Onto land. The end of the Devonian saw the late Devonian extinction event, followed by a gap in the fossil record of some 15 million years at the start of the Carboniferous, called Romer's Gap. The gap marks the disappearance of the Ichthyostegalian forms as well as the origin of the higher labyrinthodonts. Finds from this period found in East Kirkton Quarry includes the peculiar, probably secondarily aquatic Crassigyrinus, which may represent the sister group to later labyrinthodont groups. Early Carboniferous saw the radiation of the family Loxomatidae, a mysterious group that may have been the ancestors or sister taxon of the higher groups. By the Ordovician age of mid-Carboniferous times, the Labyrinthodonts had radiated into at least three main branches. Recognizable groups are representative of the temnospondyls, lepospondylus and reptile-like amphibians, the latter which were the relatives and ancestors of the Amniota, while most labyrinthodonts remained aquatic as semi-aquatic. Some of the reptile-like amphibians adapted to explore the terrestrial ecological niches as small or medium-sized predators. They evolved increasingly terrestrial adaptations during the Carboniferous, including stronger vertebrae and slender limbs, and a deeper skull with laterally placed eyes. They probably had watertight skin, possibly covered with a horny epidermis overlaying small bony nodules, forming scutes, similar to those found in modern caecilians. To the modern eye, these animals would appear like heavy-set lizards, betraying their amphibious nature only by the lack of claws and by spawning aquatic eggs. In the Middle or Late Carboniferous, smaller forms gave rise to the first reptiles. In the Late Carboniferous, a global rainforest collapse favored the more terrestrially adapted reptiles, while the many of their amphibian relatives failed to re-establish. Some reptile-like amphibians did flourish in the new seasonal environment. The reptilomorph family Diodectidae evolved herbivory, becoming the largest terrestrial animals of the day with barrel-shaped, heavy bodies. There were also a family of correspondingly large carnivores, the Limnoselidae, that flourished briefly in the Late Carboniferous heyday of the Labyrinthodonts. The herbivorous Diodectidae reached the maximum diversity in the Late Carboniferous, early Permian, and then quickly declined, the role taken over by early reptilian herbivores like parasaurs and edaphosaurs. Unlike the reptile-like amphibians, the temnospondyli remained mostly denizens of rivers and swampland, feeding on fish and perhaps other labyrinthodonts. They underwent a major diversification in the wake of the Carboniferous rainforest collapse, and they too subsequently reached the greatest diversity in the Late Carboniferous and early Permian, thriving in the rivers and brackish coal forests in continental shallow basins around equatorial Pangaea and around the Paleozoic Ocean. Several adaptations to piscivory evolved, with some groups having crocodile-like skulls with slender snouts, and presumably had similar lifestyle. Others evolved as aquatic ambush predators, with short, broad skulls that allowed for opening the mouth by tipping the skull back rather than dropping the jaw. In life they would have hunted rather like the modern-day monkfish, and several groups are known to have retained the larval gills into adulthood, being fully aquatic. The Metoposauridae adapted to hunting in shallows and murky swamps, with shaped skull, much like the Devonian ancestors. In Euramerica, the Lepospondylii, a host of small, mostly aquatic amphibians of uncertain phylogeny, appeared in the Carboniferous. They lived in the tropical forest undergrowth and in small ponds, in ecological niches similar to those of modern amphibians. In the Permian, the peculiar Anectridia found the way from Euramerica to Gondwanaland declined from the middle of the Permian. The climate dried up, making life difficult for the amphibians. The terrestrial reptiliomorphs disappeared, though aquatic crocodile-like Ambolomeri continued to thrive until going extinct in the Triassic. The diverse lepospondyle inhabitants of the undergrowth disappear from the fossil record, among them the snake-like Astopoda. With the close of the Paleozoic, most of the Permian groups disappeared, with the exception of the Mastodonsauroid and Metopusaurid families and the curious Plagiosauridae, who continued into the Triassic. In the early Triassic, these families enjoyed a brief renaissance in the waterways of continental shallows, with large forms like Thusuchus, Benthosuchus and Eriosuchus. Their ecological niches were probably similar to those of modern-day crocodiles, as fish hunters and riverside carnivores. All groups developed progressively weaker vertebrae, reduced limb ossification, and flatter skulls with prominent lateral line organs, indicating the late Permian, early Triassic temnospondyls rarely if ever left the water. An extremely large brachioropid is estimated to have been 7 meters long, and probably just as heavy as the Permian Prionosuchus. With the rise of the real crocodiles in the Middle Triassic, even these temnospondyli went into decline, though some hung on to at least early Cretaceous on the southern Gondwanaland, in regions too cold for crocodiles. Origin of modern amphibians. There is today a general consensus that all modern amphibians, the Lissamphibia, have their origin in Labyrinthodont stock, but this is where consensus ends. The fragile bones of the Lissamphibians are extremely rare as fossils, and the modern amphibians are highly derived, making comparison with fossil Labyrinthodonts difficult. Traditionally, the Lepospondyli has been favored as Lissamphibian ancestors. Like the modern amphibians, they were mostly small with simple vertebrae, resembling Lissamphibians in many aspects of external anatomy and presumably ecological niches. At a subclass level, it was thought that Labyrinthodonts gave rise to Lepospondyls, and Lepospondyls to Lissamphibians. Several cladistic studies also favor the lepospondyl link, though placing Lepospondyli as close relatives or even derived from reptile-like amphibians. One problem with this position is the question of whether Lepospondyli actually is monophyletic in the first place. Temnospondyl affinity for the Lissamphibia is suggested by other works. The temnospondyl family Amphibians has been considered a possible candidate for the ancestors of Lissamphibians. The Amphibian Gerobatrachus, described in 2008, was proposed to be a transitional form between temnospondyls and aneurons and chordatans. It possessed a mixture of aneuron and chordatan features, including a broad skull, short tail, and small pedicellate teeth. Complicating the picture is the question of whether Lissamphibia itself may be polyphyletic. Though a minority view, several variants have been forwarded through history. The Stockholm School under Gunnar Save Soderberg and Eric Jarvik argued during much of the 20th century that amphibia as a whole is biphyletic, based on details of the nasal capsule and cranial nerves. In the view, lepospondyls are ancestors of frogs, while salamanders and caecilians have evolved independently from Porelepiform fish. Robert L. Carroll suggested the tailed amphibians are derived from lepospondyl microsaucent frogs from temnospondyls. The cladistic analysis of Gerobatrachus suggests salamanders and frogs have evolved from temnospondyl stock, and caecilians being the sister group of the reptile-like amphibians, rendering Lissamphibia itself an evolutionary grade relative to the remaining tetrapod classes. A consensus on origin of Lissamphibians and relationship between the various Labyrinthodonts is not likely to materialize soon.